Now we move on to the next wave transformation phenomena. We are going to look at wave refraction. Now, wave refraction occurs when the wave moves from transitional to shallow water. That is the region when the wave begins to fill the seabed, to fill the bottom more and more. So when the wave fills the bottom, it responds. How does it respond? Okay, as we call, when DOL reduces, when the relative depth reduces, then the wave celerity reduces and the wave particle motion increases. So since the wave celerity decreases, if we look at this figure, it tells us that when the wave is moving at a certain angle towards the shoreline, the side here haven't filled the bottom, but the side here filled the bottom first. This is the same wave that propagates all the way from offshore region, now approaches the shoreline. This same wave, this part haven't filled the bottom, but this part filled the bottom first. So the part that filled the bottom first will slow down first. The part that haven't filled the bottom slows down later. And as a result of that, when a wave approaches a shoreline, it is very similar to the effect of a beam of light approaches an interface. And let's imagine this side is the air and this side is a perplexed glass. So a beam of light will be refracted like this, and the same thing actually happens to the wave. A wave that approaches shallow water, assuming that this part is deep, this part is shallow, it will be refracted so that it actually becomes moving in a direction which is increasingly normal to this interface. Originally it is coming at an oblique angle, but due to refraction it becomes more normal to the surface. Normal meaning 90 degree. So a wave that comes in this direction, for example, is refracted so that the refracted part becomes normal to the shoreline, and eventually the wave all arrive at the shore, normal to the shoreline. So the consequence is wave crest will bend to approach the orientation of the bottom contour, assuming that the bottom contour, the changes of the water depth is parallel to the shoreline. This figure shows a very interesting phenomena of refraction. Now let's assume this part is deep water and this part shallow water. We notice that the wave energy enters into this small lagoon through this opening, and the wave is only coming from a single direction. It's not very clear, but maybe you can tell that the waves are actually aligned in this direction. So it is the waves actually moving in this direction into the lagoon. But when it moved into the lagoon, because the water depth is shallow, it started to undergo refraction. And the refraction causes the wave to align itself and eventually becomes normal to the shoreline. So you notice that the wave approaches the shoreline in a 90-degree direction. It moves in this direction, normal to the shoreline. Of course, the wave crest becomes more or less parallel to the shoreline. The direction of movement is almost 90 degrees or normal to the shoreline. Okay, so that's the effect of wave refraction. So as the wave approaches the shore, we have one common way of representing that graphically. We will use the straight line to represent the wavefront parallel to the wave itself, and we will use an orthogonal line which is more or less perpendicular to the wavefront. Okay, so on the previous slide, the orthogonal is shown as red as well. Okay, here orthogonal is shown as red. Okay, as we mentioned, the waves is refracted and becomes increasingly perpendicular to the shoreline, whereas the wavefront is parallel to the wave. Right, so they are in the perpendicular direction. So wave orthogonal is drawn typically in such a way that it divides the wavefront into segments of equal energy flux, such that no energy propagates along the crest. What does it mean? So for example, here we draw this orthogonal, the red line, and we draw another orthogonal, another red line. Now, the orthogonal typically is drawn in such a way so that the wavefront from this point to this point has a certain amount of energy between the two orthogonal, and by the time the wave arrives here, the wave from this point to this point in between these two orthogonal still have the same amount of energy. So that's what we mean by the orthogonal divide the wavefront. The wavefront is basically infinite in order in this direction, but we divide it so that in between two orthogonal, the energy inside here is always the same. This is a very important concept for the study of wave refraction, because as the wave orthogonal converge or diverge, as we will see later, the energy and as a result the wave height increases or decreases. Let's look at this figure over here. We have a wave over here which is moving towards a shoreline which is curvy like this. We're going to assume that the bathymetry, which means the water depth, changes linearly with the distance from the shoreline, such that the further and further away from the shoreline, the water depth becomes deeper and deeper, but in the same rate. So for example, let's say this dashed line here is 5 meters deep. It is the same distance away from the shoreline. Let's say this dashed line here represents 10 meters deep, and it is the same distance away from the shoreline. So the shoreline, the bathymetry is parallel to the shoreline. The further the distance from the shoreline, the deeper the water is. Okay, now these are the orthogonal. Okay, so now what we're going to do is that we're going to examine what happened to the orthogonal. Alright, so if we look at this orthogonal is increasingly refracted so that it becomes more and more perpendicular to the shoreline. This orthogonal is also refracted and become more and more perpendicular to the shoreline. This did not get refracted. Okay, why? Because if you notice, the wavefront, this is the wavefront. The wavefront that moved here in this part, the left and right are the same water depth all the time. So it didn't experience any refraction and it reached the shoreline. Whereas for this orthogonal, the wavefront is on the left and right of this orthogonal. You notice that when it arrives here, the left hand side fill the bottom faster than the right hand side. So the left hand side slow down first. The right hand side still continue to move forward. So the wavefront becomes distorted and becomes more and more in this direction, so that eventually the wavefront becomes parallel to the shoreline, whereas the orthogonal becomes perpendicular to the shoreline. So if this one, the left side fill the bottom first, and so that it reflects towards here, this one, the right side fill the bottom first and it reflects towards here. And so in general, we notice that if there is a bay like this, then the orthogonal will spread out Whereas if there is a headland like this, the orthogonal will converge. In a way like this, the orthogonal diverge. When orthogonal diverge spread out, then you notice that the distance between the two orthogonal becomes wider. When the distance becomes wider, what happens is that since the total amount of energy in the between two orthogonal is the same, so the same amount of energy between these two orthogonal now is spread out over a larger distance, so the wave height will drop here due to the larger distance between the two orthogonal. Whereas over here, the same amount of energy between the two orthogonal, when it reaches closer and closer to the shoreline, it is concentrated in a shorter distance. So as a result of that, the convergence between the two orthogonal, which cause it to become narrower and narrower, will cause the wave height to increase. So wave height generally will increase when the wave approaches a headland, and the wave height generally will decrease when it approaches a bay. So based on the figure itself, we also will be able to relate mathematically, as we will discuss later, how the width B changes from the deep water condition B0 to the width B in the shallow water region. Of course, the changes happens alongside the changes in the wavelength. In the deep water, the wavelength is L0. By the time the same wave arrives at the shallow water, the wavelength becomes L. So the changes from L0 to L happens together with the changes of B0 to B, whereby B is the distance between two orthogonals. These figures here, we pick the concept we have just discussed, whereby we see the convergence at the headland on the left and the divergence on the right. The convergence on the left is expected to cause the wave height to becomes higher. The divergence on the right is expected to cause the wave height to becomes lower. One of the effects of this convergence and divergence is coastal erosion. The convergence will cause higher wave height, and the higher wave height is able to erode the headland. The divergence is going to reduce the wave height, and because the wave height reduces, then this region are more likely to have less energy, and so it becomes a location whereby the coastal sediment will be deposited. Right now we are going to introduce the refraction coefficient KR. Now we consider a wave train approaches the shoreline where the energy flux between two orthogonals remain a constant, as we discussed previously. So we modify the equation a little bit, so such that now we write it as BNE over T equals to constant. That means the total amount of energy in a width of B between two orthogonals will always remain a constant when it moves shoreward. So as previously, what we did, we are going to substitute E, the wave energy, in terms of this expression. And since BNE over T equals to constant, so the value on one location is always the same as the value on another location. Now rho G and 8 are cancelled on both sides of the equation, so that we have B1 N1 H1 squared times L1 equals to B2 N2 H2 squared times L2. So for location 1, we're going to replace it with the offshore deep water location, so that B1 becomes B0, N1 becomes N0, H1 becomes H0, and L1 becomes L0. whereas B2 and H2 and L2 is going to represent the value in any other location that we are interested in. We drop the subscript so that we write them as B, N, H, and L only. So after rearrange the entire equation, the equation will look like this. It is very similar to the Scholling equation that we see previously. We have H over H naught on the left hand side. We have the Scholling coefficient on the right hand side, but now we have one additional term, which is the square root of B naught over B. So if we simplify this expression, right now basically H over H naught is equals to this part is the Scholling coefficient, right? And this part is the refraction coefficient. The Scholling coefficient, as we know previously, is H over H naught prime, and basically the refraction coefficient is the square root over B naught, square root of B naught over B. Right? So as the wave moves shoreward, we know that the Scholling coefficient tend to become larger than 1 in the shallow water region, but generally the refraction coefficient is likely to be less than 1. Now, whether the wave height actually increase or decrease, that means how the H compared to the H naught, actually depends now on what is the value of these two coefficients, which of course depends on the local bathymetry and the coastal profile, which means that it is actually a combination effect of both Scholling and refraction. The refraction equation that we looked at previously try to relate the effect of refraction in terms of the change of wave B between the orthogonals when the wave propagates towards the shore. Right now, in this slide, we're going to look in terms of the change of angle. We're going to apply the Snell's law to analyze the refraction. So again, we're going to look at the process of refraction using this figure. Let's assume that here this is the incoming wave, this is the wavefront, okay, and these two are the orthogonals, and they are approaching the shallow water, okay, demarcated by this straight line, so that the area above here is has a water depth of D1, whereas the area over here has a water depth of D2, assuming that the change is sudden. Okay, so when the wave front approaches this change of water depth, this side fills the bottom first, and so this side slow down, and so changes, slow down, and it's refracted, and subsequently these are the reflected wave front. Okay, and this is the orthogonal, which now has been refracted so that it is oriented in the normal direction to the shoreline, assuming that this change of water depth is parallel to the shoreline. So we're going to examine this angle over here. If this alpha 1 is the angle of the incoming wave, and alpha 2 is the angle of the refracted wave, then we are able to construct this triangle over here, and also this triangle over here, which shares the same side over here, where the distance is assumed to be x. Okay, so let's look at this triangle on the incoming wave. We can write this as sine of alpha equals to L over x. Okay, so sine of alpha equals to this L divided by this x. On the figure, it used alpha 1 and L1. In this equation here, we use alpha naught and L naught to suggest that this location 1 is a deep water location. If we look at the next triangle, sine of alpha 2 is equals to L2 over x. So if we drop the subscript, sine of alpha is L over x. Okay, after rearranging, that's how it looks like. So basically, these expressions, okay, are derived from these two triangles, which involve the change in the direction of the wave propagation when the wave moves from a water depth of D1 to another water depth of D2. Of course, the derivation here assume that the change of water depth is sudden, so we need to also make a statement that we ignore any reflection from the step. Of course, in actual sea, they may or may not have a step. If there is a step, there may be a reflection effect from the step, but we're going to ignore that in this particular analysis. So based on this expression that we derive, we are then able to rearrange it and obtain this expression. Okay, as you can see from here, what we get is that sine alpha over sine alpha naught must be equals to L over L naught. And since L and C are directly related, we remember that C is basically equals to L over T. T is a constant. So L over L naught is also equals to C over C naught. So this equation tells us that if a wave propagates from deep water to a shallow water so that the angle alpha naught change to alpha, then the wavelength L naught will change to L and the wave celerity C naught will change to C. If we are able to relate the change of wavelength when the angle of the orthogonals changes, then we will also be able to relate the change of the width between two orthogonals, as which will be done on these particular slides. Here we see that there are two orthogonals which are refracted as the wave propagate towards the shoreline, moving from deep water to shallower and shallower water, whereby the bathymetry of the water changes parallel to the shoreline. So what we see here is that, for example, from the changes of water depth here to the water depth here, the wave front make an angle of alpha naught to the bathymetry, and the angle change to alpha after refraction. The width between the two orthogonal is B naught before refraction, and it is B after refraction. So we use the same approach as the Snell's law just now. We can write cos alpha naught equals to B naught over x. X is this distance between point B and point C. And likewise, cos alpha will equals to B over x. That is how we get these two expressions, which now relates the width between orthogonals. Since we already defined the refraction coefficient as the square root of B naught over B, so now we can obtain expression from here to write the refraction coefficient in terms of square root of cos alpha naught over cos alpha. Why are we doing that? Because if we, for example, take a satellite photo of the wave, or we go to the beach and observe the wave, it is easier for us to measure or approximate the change of the incidence angle alpha rather than to try to measure B and B naught on site, which is actually impossible. So by defining KR now as the change of incidence angle rather than the change of the width B, so it is much easier for us to quantify KR. So if alpha naught is the incidence angle of the deep water wave, which can be obtained based on offshore wave observation, then alpha can be obtained from nearshore wave observation, or it can also be obtained from the previous slide by rearranging the previous slide so that we can obtain alpha as the arcsine of COC naught times sine of alpha naught. Right now let us look at an example. Consider the wave from examples 4.6-1 and 4.6-2, which has a deep water wave height of 2 meters and a period of 10 seconds. Assume the wave crest in deep water are oriented at an angle of 35 degrees with the shoreline, and that the nearshore bottom contours are essentially straight and parallel to the shoreline. Determine the wave height and crest orientation with respect to the shoreline when the wave propagates into water 2.3 meter deep. So again, this example is actually a continuation from our earlier example. So we are going to look back at these two examples, 4.6-1 and 4.6-2. We are given the deep water wave period is 10 seconds, so we should be able to work out the C naught is 15.6, whereas at 2.3 meter deep, the C is 4.75 meter per second. Of course, that also means that we can get L naught and L as well. So if the deep water wave is approaching the shoreline at 35 degrees, what would be the angle of approach when it reaches this water depth? The angle would have changed due to the refraction effect. So we calculate the angle using this expression. Right, we have C and C naught, we have alpha naught. So we found out that the angle has now reduced to 9.5 degrees. This 9.5 degrees is the angle of the wave front to the line which are parallel to the shoreline. So which means that the angle becomes smaller and smaller. Eventually it will become 0, very near to the shore. So that means the wave front would be almost parallel to the shoreline, whereas the wave orthogonal will be normal to the shoreline. Of course, we have used C over C naught here in the equation. Actually, we can equally use L over L naught. It will be the same based on the derivation that we have shown earlier. Since we already know the incidence angle of the deep water wave, which is 35 degrees, and also the incidence angle of the wave by the time it reached the water depth of 2.3 meters is 9.5 degrees. So we are now able to work out the refraction coefficient, which gives us the value of 0.91. So in order to determine the wave height at this particular location, we now apply the complete equation, which is made up of the Scholling coefficient multiplied by the refraction coefficient in order to give us the change of the wave height compared to the deep water wave. So we have discussed how to obtain the value of the Scholling coefficient, which basically is the L naught and L and N value. So if we solve this, you notice that the final wave height is 1.166. That means higher than the deep water wave height. So given the deep water wave height is 2 meters, so at this location we expect the wave height to become 2.33 meters.